So critical points are where the derivative equals zero or does not exist. And on number one here, we're given that this is the graph of f prime, meaning it is already our derivative graph. Okay, so if we want to know where f has critical points, that's where this graph equals zero or doesn't exist. And so there are critical points at x equals, and then there's two places where this graph equals zero. 1 and 3. And then also when x is equal to 4, we have, because this is an open circle, f prime, this graph does not exist. So there's also a critical point for f at x equals 4. We don't need to worry about the endpoints because the endpoints here are not open circles, meaning the points do exist. If f prime does exist, then we don't need to worry about it being those being critical points for f. So it's just those three for, I do need to explain, sorry, for critical points. So 1 and 3, and I'll say because f prime equals 0. And for 4, I'm going to say because f prime does not exist. Okay. And then for number 2, here we have a function. This is a polynomial function. For polynomials, they are differentiable everywhere, so there's nowhere where the derivative doesn't exist, meaning for critical points, for g, I only need to figure out where g prime equals 0. Okay, so where g prime equals 0. G prime is 6x minus 8, so I'm going to set that equal to 0. And so 6x equals 8, x equals 4/3. So this is our only critical point for g. Okay, for number 3, we are sketching a graph that meets these requirements, and you could have something that also meets requirements but might look a little bit different from mine. I'm going to put, one second here, I'm going to put units on here. Oops, -3, 3. All right, we'll kind of fill in around this as needed. So it only exists from -3 to 6. That's my domain. Absolute max at the left endpoint. So I'm going to put a higher point here at -3 something. Relative min at x equals -1 and x equals 3. So it has a min. I'm just going to put a dot here and a little curve like that. And then also at 3, and it does not have to be the same. Actually, I'm going to put it up here just for fun. Okay, so a min at 3. Absolute min at x equals 5, so could be also a local min, but doesn't have to be. It does have to be lower than the other ones there. I'm going to do that. Okay, and then an undefined derivative at x equals 0. Because the graph is from -3 to 6, I'm not going to do an asymptote. I'm just going to do a cusp at 0. So whatever is happening at 0, it's going to be a sharp turn, which is fine. So, all right, and I'm going to fill in everything around this. So we'll have a local min here, and then, oh, I guess I missed that point. That's okay. And then a cusp, and then another local min, and then absolute min, and then it stops at 6. Something like that will work. Yours does not have to look like mine. Mine looks a little bit funky, but it does meet all the requirements of having the extrema, the absolute and relative extrema at all of those points. Okay, number 4, multiple choice. It says f is continuous from -2 to 1 and closed interval and differentiable on -2 to 1 the open interval. F of -2 is -5 and f of 1 is 4. What could be true? Okay. Well, let's see. I'm going to go through all 5 of these, even if I find the one that could be false. Okay, so there exists a c in between -2 and 1 such that f of c equals 0. It's continuous and differentiable, and we are going from a negative to a positive, so there's no reason. Nope, actually, let me say that differently. Because of the IVT, it has to equal 0 somewhere because 0 is between -5 and 4. So it's not that one. B, there exists a C from between -2 and 1 such that the derivative is 0. The derivative existing does not tell us whether or not we have a place where the derivative equals 0. So could be this, coming back to that. There exists a C from -2 to 1 such that f of C equals 3. That's also an IVT conclusion because 3 is between -5 and 4. There exists a C between -2 and 1 such that the derivative is equal to 3. Is there any reason that we know that the derivative has to be equal to 3? Nope, we don't know anything about the derivative. And then for E, there exists a C on the interval from -2 to 1 closed here such that f of C is greater than or equal to f of x for every x in the interval. This one has to be true because this is the conclusion of the extreme value theorem, okay? Because EVT says that there has to be a max, and that's what this is stating, that f of C is greater than or equal to f of x for all the x in the interval. So that's by the EVT. Okay, so coming back to these two, the only way to know something about the derivative, okay, based on our information, is by the mean value theorem, which we did in 5.1. That was the last thing that we covered back in December, I know, a whole year ago. And so let's go ahead and do the average rate of change and figure out if we get one of these conclusions from that. So if I do f of 1 minus f of -2 over 1 minus -2, I'm going to get 4 plus 5 over 3. 9 over 3 is 3. So this one does have to be true by the mean value theorem, meaning the only one that doesn't necessarily have to be true is B. And that is our only that's our answer. Okay. Okay. And then another multiple choice question here. F is continuous on the closed interval and differentiable on the open interval. What could be false? Once again, based on those conditions, I know that EVT, the extreme value theorem, and the mean value theorem both have to apply. So f prime of C is equal to f of B minus f of A over B minus A for some C inside the open interval. That one is true by the mean value theorem. The derivative is equal to 0. Is there a place where the derivative has to be 0? Nope, I don't think so. Does f have to have a minimum? Yes, that's true by the extreme value theorem. Does it have to have a max? That's also true by the extreme value theorem. So the only one that could possibly be false is B. Okay, and then another multiple choice here. So f is defined on the closed interval from 0 to 1 and satisfies f of 0 equals f of 1/2 equals f of 1. On the open interval 0 to 1, f is continuous and strictly increasing, okay? Which of the following statements is true? If you have not tried this one yet, try it. Pause the video, try it. Hopefully you're trying all of these before you're watching the video, but give it a try first. This one's a little bit tricky. Okay, so the way to make this one work, put 0, 1/2, and 1. I need 3 points that are the same height, okay, because I know that those 3 are the same. It also says that the function is continuous and increasing everywhere. The only way for that to work is if we don't worry about what's happening at the endpoints, which this is an open interval. This one is closed, so I can draw it like this. And it really doesn't matter which direction it curves. I just need to be increasing everywhere and pass through that point right there. Okay, so looking at this graph, A, f attains both a minimum value and a maximum value on the closed interval. Not necessarily, because we only know that it is continuous on the open interval, and my picture is a counterexample to that, so that one is not necessarily true. F attains a minimum value but not a maximum. Once again, not true. F attains a maximum but not a minimum. Once again, not true. So all 3 of these would need the extreme value theorem, which requires continuity on the closed interval, and we do not have that. D, f attains neither a min nor a max on the closed interval. That one is true. Okay, because, and again, something like this with open endpoints on both of these, and then, you know, the 3 points right here is the only way the only way to do this. Okay. Last one, we have a function g of x and k is a constant here, and we want to know for what value of k does g have a critical point. Once again, critical point means the derivative equals 0 or does not exist. This is a differentiable function no matter what k is. For any number, x squared is continuous and differentiable everywhere. E to the something times x is continuous everywhere. So we really only need to worry about where g prime does not exist. So let's find g prime. And what rule are we using? Yep, I know you said product rule. Okay, so 2x e to the kx plus x squared e to the kx times k. I also needed to use the chain rule when I did the derivative of this part. And then I'm going to factor e to the kx out of this. So I have 2x plus k times x squared left over. And I want to know for what value of k does g have a critical point at x equals 3/2. Okay, so that means when x is equal to 3/2, I need this to be equal to 0 because this whole expression has to be equal to 0, and e to the kx for any value of k can never be 0. So plugging 3/2 into here, I get 2 times 3/2 plus k times 9/4 is equal to 0. So that's a 3. So I get k times 9/4 equals subtracting -3. So k is equal to -4/3, which is a. Okay, if you have any questions, let me know.